Start. Okay. Examples team. Find find power series representation for the functions. First one is this 1 over 1 minus x squared. Second one is 1 minus x cubed, and the third one is ln 1 plus x by starting from the geometric series 1 over 1 minus x, which is equal to this series 1 plus x, 1 plus x squared, and so on, right? And we know that this is convergent for x less than 1. İsterseniz şöyle yazayım. Yani x eksi 1 ile 1 arasında olduğu zaman convergent the power serisi. Geometric series, this is convergent only for x equals from 1 to minus 1. Okay, now how can we do this solution? So what is the question? Question is start from this and obtain power series representations for these functions. Well, this one 1 over 1 minus x squared, you may think it both ways. It is either the square of this, so you take this function and multiply with itself. You can do it that way, or you can take derivative of this, right? When you take derivative, you get again 1 over 1 minus x squared, right? So you can do both things. Now this is true, so just take the derivative of the above power series. Değil mi? Şimdi soru neydi? Bu power serileri için özür dilerim. Bu fonksiyonlar için power seri representation'lar istiyoruz. Ve soru şey diyor, hani onları bu power seriyi kullanarak elde edin. 1 over 1 minus x'in power serisini kullanarak elde edin. Biz de ne gözlemledik? Bu ifadenin türevini alırsak, so I can take the derivative. Remember the theorem tells us the following. Whenever a power series is convergent, then its derivative is also convergent on the same interval, open interval. So since this is convergent on the open interval minus 1 to 1, its derivative will be also convergent on the same interval. And I can take the derivative term-wise. So derivative of this is just the derivative of this, which is just what? Derivative of 1, 0. Derivative of x is just 1. Derivative of 2x squared, 2x. And then derivative of x cubed. And so on. N times x to the power n minus 1. And this way. Okay. And this is true for x again between 1 and minus 1. Okay. Theorem guarantees that. What about the derivative of this expression? Well, this is a function and its derivative is just what? 1 times this 0. So derivative of 1 times 1 minus x, which is 0, minus this guy times derivative of this. It's another minus 1. So I get just 1 over 1 minus x squared. And this is equal to 1 plus 2x plus 3x squared. Okay. So we obtained a power series representation for this function, 1 over 1 minus x squared. What about the other one? So this is a, right? A mi demiştik ona? Evet, a. So this is a. For b, it is 1 over 1 minus x cubed. Well, it is the derivative of this gadget. I can take derivative one more time. So let's take derivative again. 1 minus x squared derivative. What is this? This is just 0 plus 2 plus 6x plus bundan önceki ne olacak? Burada 4x cubed vardı. 12x squared and so on. N times n minus 1 to the power n minus 2 plus so on. So minus 1 and this. What about this? This is just 2 over minus this, right? Şimdi bu x 1 eksi x'in eksi ikinci kuvveti eksi 2 aşağı inecek. İçinin integral türevi oradan da eksi geldi. Küp. Okay. Derivative of this is just 2 over 1 minus x cubed and it is just 2 plus 6x plus 12x squared n times n minus 1 x to the power n minus 2 and so on. So 1 over 1 minus x cubed is just 1 plus 3x 6x squared and so on, n times n minus 1 over 2. Okay. All right. What about the last one, which was logarithm 1 plus x? Well, logarithm is just the integral of this gadget, right? Integral of 1 over x is just ln x. Here I have minus, here I have plus, so I have to make a little trick. The trick is this. Since 1 over 1 minus x is this, and this is true for all x between 1 and minus 1. Okay, the trick is this: just replace x by minus x, right? If x is between 1 and minus 1, minus x is also between 1 and minus 1. So in this expression, I replace x by minus x. So if I do that, I will get, then we get When I plug minus x here, I will get plus x. I plug minus x for x, so I get 1 minus x, and then minus x squared minus x cubed, and so on. This time minus x between 1 and minus 1. And what we get is 1 minus x plus x squared minus x cubed plus x to the 4, and so on. Minus x between 1 and minus 1. If you just multiply everything by minus 1, you get minus 1 x 1 again, right? So I have this. And then we do what? Well, this is a function, continuous function on this interval, right? 0 is here, minus 1 and 1 here. Okay, for any x, let me just do this. Integral dt 1 plus t from 0 up to x. Okay, well, what is this? This is the integral from 0 to x of 1 over dt. 1 over dt is what? 1 over, 1 over 1 plus t. 1 over 1 plus t is this, 1 minus t plus t squared minus t cubed, right? Goes like this. And then I have dt, right? And the theorem tells me the following. If you have a convergent power series, then you can integrate it as if it's a polynomial, right? Term-wise integration. Integral of 1, it is just t. Integral of t, it is t squared over 2. Integral of t squared, t cubed over 3, t to the 4 over 4, and so on. I will compute this at 0 and x, right? Because I integrate from 0 up to x. Here x is again between minus 1 and 1, right? Like this one. X is somewhere between 1 and minus 1. Okay, what is the result? When you plug x, you get x here. When you plug 0, you just get 0, right? So the result is just this. So it goes like this. I can write it as a sum also, and from 1 to, okay, uh, 1 to infinity, there is no 0 term, minus 1 to the power n minus 1 x to the power n over n, right? Let's check. When n equals 1, you get minus 1 to the power 0, which is 1, times x divided by 1, which is x. When n equals 2, you get minus 1 to the power 2 minus 1, which is minus 1, x squared over 2. So you get this term. When n equals 3, you get this term, and so on. So I have this. What about this gadget? Well, this is just ln x, right? No, sorry, ln t, ln 1 plus t, right? And then 0 and x. When you plug x, you get ln 1 plus x minus ln. When you plug 0, you get just ln 1. But ln 1 is just 0, and this is ln 1 plus x. And this is again true if x is between 1 and minus 1. Okay? Uh, so we used all the theorems actually so far. Right? We used all the theorems we stated so far, except Abel's theorem. Now let's see how we can make use of Abel's theorem. Suppose that we want to compute ln2 as a infinite sum. So let's compute ln2. Okay. Well, I can plug 1 here. I will get ln2. But the question is, here x is between 1 and -1. Okay. So I cannot let right away x equals 1 because it is not allowed. The theorem for differentiation and integration works for open intervals. So how can I plug 1 here? Well, I'll do the following. I'll use Abel's theorem. Abel's theorem tells us the following. If I have a power series, it is continuous at all the points. It is what? It is convergent. Well, so if this is convergent at x equals 1, then I can plug 1 here and 1 here. Okay, so Abel's theorem guarantees that. So let's see. Uh, let's check first if the series is convergent at the end points. The other endpoint x equals -1 actually is not is not something I am interested in, and actually it doesn't it is not convergent either, right? For x equals -1, you cannot plug it here, it doesn't work, and you cannot plug it here. Why is that? You see what is the result for x equals 1? You get -1 to the power n, -1 to the power uh, n, right? X equals -1 divided by n. So this is just -1 to the power 2n minus 1. So it's an odd number. So it is always -1. So this is nothing but this actually. And this is the harmonic series and it is divergent. Okay. Divergent since it is the harmonic series. What about x equals 1? -1 to the power n divided by n. Pardon, tam öyle değil. -1. Okay. X yerine 1 yazarsanız, when you plug 1 for x, you just get 1 over n, and the coefficient is -1 to the power n minus 1. So you get this. What is this? This is an alternating series, right? So this is 1 minus 1 over 2 plus 1 over 3, 1 over 4. We already saw that this is convergent, right? This is convergent by the alternating series test. I have done the details of this last week, so I will not repeat it. But of course, in the exam, if you are given such a question, then you are asked to write down all the details. Since I have written the details last week, I don't do it today, but you have to check the conditions of alternating series test are satisfied. What were they? An should be alternating. Well, it is 1 minus 1 over 2 plus 3, 1 over 3, and so on. 1 minus 1 positive term. It should be decreasing with limit 0, right? It is decreasing with limit 0. Therefore, it is convergent. And Abel's theorem tells us that whenever you have an equality like this, and if it is convergent at the end point like this, then this function is continuous. Continuous means you can let x goes to 1 and the value at x equals 1, at the limit at equals 1 is just the value of the function at x equals 1. In other words, you can plug 1 here and 1 here, and two sides will be equal to each other. Okay? Because this is a continuous function, this is also a continuous function. They are equal at the open intervals, but since they are both continuous, you can take limit as x goes to 1 for both of them. The limit as x goes to 1 for this one is ln 2. The limit for this as x goes to 1, well, you just plug x equals 1, okay, since it is continuous. So Abel's theorem guarantees that finally, by Abel's theorem we have, isterseniz şöyle detaylıca yazayım bir kereliğini. ln2 is this, ln 1 plus 1, or şöyle yazayım, limit as x goes to 1 ln 1 plus x, right? I have this equality because the logarithm function is continuous. And then I have what? This is equal to limit as limit of the series as x goes to 1 neydi? X'i 1 üzeri n eksi 1 çarpı neydi? Dur. X üzeri n bölü n. X üzeri n bölü n. Why do we have this? So this is, let me write the reasons why these are, why do we have these equalities? Since ln x is continuous. And this is true what? Well, this is true because of the definition of limit. Limit as x goes to 1 means x is getting closer and closer to 1, but it is never equal to 1. So as x goes to 1, x is not equal to 1, but it is very close to 1. But we know that if x is not equal to 1, if x is not equal to 1, these are equal, right? This thing is the same as this thing, as if x is not 1, but very close to 1. Okay, so instead of this, I can write this. And this is what I have done over here. Okay, this is true since x is going to 1, x is less than 1, but it is, since it is close to close to 1, it should be, larger than minus 1. Okay, şöyle yazayım belki. Since x is going to 1, we have x is between 1 and minus 1. Peki Abel'in teoremi nerede işin içine giriyor? Abel'in teoremi de şurada. Değil mi? Neydi Abel'in teoremi? Eğer if your series is convergent at an endpoint, then the limit of this is just, you let x equals 1 here. When you let x equals 1, you get this, which is just minus 1 to the power n over n, and from 1 to infinity. And this is the Abel's theorem. Abel's theorem, okay? Yeah. So you see, I mean, this looks obvious maybe at first, right? I mean, it should be like this, but why it is true is actually is not that straightforward. Okay, it uses a lot of facts we have been studied so far. Tamam mı? Hı. Şurada mı? Çünkü e, yani şu var elimizde. İntegral e, ve türevi alırken açık aralıkları koruyoruz. O yüzden bu buna açık aralıkta eşit. Ama Abel teoremi diyor ki hani convergent'sa burada endpoint'i de koyabilirsin. Ama differentiation ile integration teoremlerine bakarsan onlar açık aralıkta ifade edilmiş. Kapalı aralıkta değil. Ee, yani herhalde şunu söylemek istiyorsun değil mi? Ln 1 artı x eşittir. Şöyle yazabilirim. Eksi 1 üzeri n bölü n x üzeri n for x şunu demek istiyorsun. Tamam, bunu yazabilirsin. Hı hı. X eşittir 1'i Abel'in teoremi söylüyor. Gerisi ne biliyoruz da Abel'in teoremi de şeydir, çok kolay değil yani. Bayağı e, içinde üç kağıtlar var yani. Zor bir teorem. Çok zor değil ama hani böyle ha deyince yapılmıyor. Diğerleri yapılır da o ingenious bir adım var orada yani. Hani onu kafadan yapamam. Diğerlerini yaparım. Hani şimdi oturur hepsini yazarım ama Abel'in teoremi e, kolay değil. Efendim? Ha yok ya, zaten yapamayız yani burada. Hani diğerlerini de yaparım diyorum ama onlar hani saatler alır. Şey değil. Bir sürü şey var. Adım var. Okay, now let's see. But you know, the nice thing is that LN2 is this series, right? I mean, so we have this. So LN2 is what? Uh, şurası n-1 ama değil mi? Bunu yanlış yazmayalım. Burası n-1. Özür dilerim. Minus 1. So this is 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, 1 over 5, and so on. Okay? ln2 is equal to this. All right. What about the other examples? Another example. Find a similar power series expansion for tangent inverse of x. Okay. Well, we again, start from this. This is true for x between 1 and minus 1. Remember, arctangent x is the integral of 1 over 1 plus x squared, right? So instead of minus x, if I had plus x squared, then I would just integrate it and obtain arctangent x. But we can do this. So let minus x to be t squared. Yani minus x yerine t squared yazıyorum. Then we get what? Then we have what? 1 over 1 plus t squared is just 1 minus t squared plus t to the power 4 minus t to the power 6 değil mi? X yerine eksi t kare yazıyorum. Yani isterseniz şöyle diyeyim. Eksi t kare. T to the power 8, t to the power 10, and so on. Here, of course, minus t squared should be 1 and minus 1. Of course, this is the same thing as saying t squared between 1 and minus 1, right? So we have this. And then we do what? Well, I can just integrate this from 0 to x. And this integral is just what? Integral of this expression. What is the integral of this? It is t, and then this is t cubed over 3 plus t to the 5 over 5, t to the power 7 over 7, t to the power 9 over 9, t to the power 11 over 11, and so on, right? For t, well, t squared between 1 and minus 1, t should be also between 1 and minus 1. Tabii şunu sorabilirsiniz. You may ask the following. Well, t squared is positive, right? There is no way it can be, minus 1 over 2 or, right? Things like this. But then you can put here t equals minus 1 over 2, right? I mean, you can indeed put minus 1 over 2. The thing is that these are power series and they are convergent on intervals which are symmetric about their centers. Here center is 0. So if it is convergent, let's say at 2, it should be convergent at minus 2 because the intervals are symmetric with respect to the center. Okay, so if it is convergent for some positive numbers and if the center of the interval is 0, then it should be convergent for the negative of those numbers. And actually there is more to this. If you have a power series, let's say convergent like this, actually you can plug not only negative or positive real numbers, you can put complex numbers also. So actually it is convergent on a circle like this, on a disk like this, on the complex plane. Okay, power series, even if they are defined for only real numbers, they automatically extend to complex numbers. Okay. Okay, now we will compute this at 0 and x, and if you do that, of course, you get what? X minus x cubed over 3, x to the 5 over 5, x to the 7 over 7, x to the 9 over 9, x to the 11 over 11, and so on. When you plug 0, you just get 0. So we have this. What about this gadget? Well, this is just arctangent of t, 0 and x. And what is this? This is just arctangent x minus arctangent 0, well, which is just 0. So I have this. and this is true for x between 1 and -1. Okay. Well, we can use this to compute, for example, tangent inverse of 1 is what? Pi over 4, right? Pi over 4 is tangent inverse of 1. Well, can we put 1 here? Well, if it is convergent, yes, using again Abel's theorem. And when we plug x equals 1, we get what? 1 minus 1 over 3 plus 1 over 5, 1 over 7, 1 over 9, 1 over 11, and so on. Is this convergent? This is convergent, which is convergent by alternating series test. Why is that? Let's check. First condition, so an is what? An is minus 1 to the power n minus 1 divided by 2n minus 1, değil mi? When n equals 1, you get 1. When n equals 2, you get 3, and so on. And sign is keep changing. So an's are alternating. This is always negative. One of them is positive. The next one is negative. An's are decreasing. Değil mi? An artı birden daha büyük. Değil mi? Yes. So this is satisfied. This is satisfied. And the limit of an is 0. Well, that's also true. So it is convergent. Since this is convergent, by Abel's theorem, it is equal to this function. Finally, the equality, let's call it star, çok yaşa. This equality holds by the Abel's theorem. Değil mi? Aynı şurada söylediğim gibi. The same reasoning, right? Arctangent 1 is equal to the limit of arctangent x as x goes to 1. That is equal to this thing, and this is equal to this thing by Abel's theorem. Okay, the same reasoning. Same reasoning. But this is something very, of course, useful in practice also, because it gives you an approximation for the number pi. Okay, pi is just 4 times this. Okay. Okay, another example. Find the sum of the series and from 1 to infinity n squared over 2 to the power n by first finding the sum of the power series n squared x to the power n. And from 0, no, not 0, 1 to infinity. Diyor ki, yani önce bu power serisini hesaplayın toplamını. N square times x to the power n. And then use that and compute this. Note that in this power series, if you let x equals 1 over 2, you will get this gadget. Okay, so if I can compute this sum, then I'll just plug x equals 1 over 2 and obtain this gadget. How can we do this? Well, we will do the same thing again. Evet, şöyle diyeyim. This is 1 plus x squared and so on, right? X to the power n. Okay. Let's take derivative of this. 1. So this is true for x between -1 and 1, right? When I take derivative, I get 1 minus x squared, and derivative is just 1. Derivative of 1 is 0, and then derivative of x, which is 1, plus 2x plus 3x squared, and so on. You see, this is just n times x to the power n minus 1, and from 1 to infinity, right? 1, 2x, 3x kare vesaire. Well, this is similar to this gadget, but not exactly, right? I need another n, and I need x to the power n here. How can I do this? Well, let's multiply this by x. X times 1 minus x squared. X is just actually another power series. Which power series is this? This is just x plus 0 times x squared, 0 times x cubed, and so on, right? And this is just 1 plus 2x plus 3x squared, and so on. And I know that I can multiply two power series. This power series is actually a single term, just x, and it is convergent for all x, right? It's convergent from minus infinity to plus infinity because it has only one term, right? There is no way sum will be infinite. So this is convergent for all x. This is convergent for x between 1 and minus 1. So if I take the product will be convergent on the intersection of these intervals. This is the whole real line. This is minus 1, 1. So the the product will be convergent on the intersection of these two, which is minus 1 and 1. It means I can just multiply this function by x, and that x just, goes inside this. So this is just this gadget, and I can just write this 2x squared, 3x cubed, and so on. In other words, this is just, so I can multiply this by x, and I can take x inside. So this is just n times x to the power n, okay? And from 1 to infinity. It was n times x to the power n minus 1. I just multiplied both sides by x, and now it is x to the power n. And then I do what? So I have x over this and equals x to the power n. Well, I need n square here. So just take derivative one more time. Okay. take derivative one more time. So x over 1 minus x squared derivative. Derivative of this is what? It is just from 1 to infinity. I have n comes down, I get n squared n minus 1. Okay. And then I have still a missing x here. So let's multiply by x again. X over 1 minus x squared derivative. If I multiply by x, I will get this. But as above, this x just goes inside the summation, and it is n squared x to the power n. And this is true for x between 1 and minus 1, because all these operations work for x between 1 and minus 1. You take integration, differentiation, and multiplication. Okay? In all those theorems, uh, the radius of convergence is just either the radius of convergence of the series you integrate or differentiate, or it is the minimum of the radii of convergence of the power series you multiply. Okay, so I have this. Let's compute this derivative. This is just x times 1 minus, no, derivative of x, which is just 1 times 1 minus x squared, minus x times derivative of this. It is 2 times 1 minus x, and then derivative of inside, it is just minus 1. And then I have 1 minus x to the power 4. And this is equal to n squared x to the power n from 1 to infinity. Okay, so this is uh, şurada biraz cancellation var. X çarpı burada 1 eksi x kalacak. Artı 2x var. Değil mi? 1 eksi x'in birisi gitti. Burada 1 eksi x küp eşittir n from 1 to infinity n squared x to the power n. So n squared x to the power n from 1 to infinity is what? Burası da ne oldu? 2x, bir x de burada var. Eksi x oldu. X artı 1. Onu da x ile çarpıyoruz. Yani x çarpı 1 artı x bölü 1 eksi x'in kübü. And this is true for x between minus 1 and 1. So I can just plug x equals 1 over 2. Let x equals 1 over 2. 1 over 2, which is in this interval. I can do this. Then I get n squared 2 to the power n from 1 to infinity, right? When you plug x equals 1 over 2, you get this. And here you get 1 over 2 times 1 plus 1 over 2, and then 1 minus 1 over 2 cubed. So this is just 1 over 2 times 3 halves divided by 1 over 2 cubed. Birisi gitti. Burada 4 var. 4 ile çarptık. 3 bölü 2'yi 4 ile çarparsanız 6. So n squared over 2 to the power n, summation from 1 to infinity is equal to 6. This one? Okay, I divided by 1 minus x. This is gone, so it is 2x. Okay. I had 2x and then minus x, so it is x plus 1. I'm sorry. I went too far. Tamam mı? Sorusu olan var mı? Okay, let's say break.